Hello everyone, I am Nitish Deshpande and today I will share my research on the topic Frequency-Selective Beamforming with Dynamic Metasurface Antennas. This work was presented at the ICC conference in Montreal in June 2025. This work is in collaboration with my colleague Joseph Carlson from UC San Diego, Professor Rodrigo Castellanos from UT Knoxville, and Professor Robert Heath from UC San Diego. Let's begin by discussing the challenges in the conventional analog beamforming. As you all know that analog beamforming is essential for 5G and 6G cellular communication. And with every cellular generation, the number of antennas on the base station keeps on increasing. The conventional analog solutions include devices like time delays or phase shifters on every antenna. The bottleneck is that these devices consume a lot of power, and as the array aperture scales for 6G, the power consumption would be infeasible. So the key challenge for 6G is to figure out how to scale the number of antenna arrays in the base station to obtain the scaling in a power efficient and cost efficient manner. In our research, we proposed a solution of dynamic metasurface antenna, which is a new kind of frequency reconcilable antenna that is controlled through low power elements like varactor diodes or PIN diodes. So in a DMA, we have a waveguide where we pass the incident signal from one end and it propagates through these radiating slots. So similar to a leaky waveguide antenna, this signal propagates along the waveguide and these slots can be configured through some low power elements. So to give a simple example, consider you have a garden hose where you put water from one end and it leaks out through the knobs. So you can tune the physical dimension of those knobs to steer the water direction in different locations. So similarly, in this device, we are controlling the electrical length of these slots by tuning the resonant frequency. So in comparison with the time delay architecture, in time delay architecture, we put time delays on every antenna. But in a DMA architecture, we do not need to we do not need to put some device on every antenna. So there's a single antenna, which is the waveguide structure, and this single antenna itself has multiple slots. So we can easily scale the number of slots on this waveguide without any significant additional power overhead. So DMA is envisioned as a low cost and low power alternative to the conventional phased arrays or through time delay based arrays. Let's look at some prior work on DMAs. So much of the foundational work on DMAs was focused on modeling and analysis of this waveguide structure, especially in Duke University. The David Smith group focused on developing these fundamental models, and they also developed proof of concepts to verify those models. Quite recently, DMA has also been incorporated in cellular systems for both uplink and downlink communication. In our group, we have also focused on integrating DMAs in a hybrid architecture where the DMAs can be configured jointly as a third precoding layer on top of this hybrid architecture. There are some papers which design codebooks with DMAs. So today I'm going to focus on a very specific limitation of the DMA. So most of this prior work assumes that the DMA is configured in a narrowband setting. However, for the next generation communication where DMAs would operate in the upper midband spectrum, we would be focusing on a wideband setup. So I will first talk about some limitations of operating the DMA in a narrowband setting. So consider this plot where I show the maximum DMA beamforming gain as function of the azimuth angle. And this plot is for a fixed frequency. That is when the DMA is optimized for a fixed operating frequency. So unlike a phased array where we get uniform gain uh, for the maximum uh, for the maximum peak across all the angles, here we see that the peak occurs only at a particular angle. So why does this happen? So let's look at the beam pattern when the DMA is configured at specific angles. So in both these plots, we see that so in this plot, the target angle is 20 degrees, but we also see there is an unintended grating lobe at minus 5.7 degrees. Similarly, in this plot, when the target angle is minus 30 degrees, we see an unintended grating lobe at minus 5.7 degrees. So in both these cases, we see these grating lobes, and we try to figure out why this grating lobe is occurring. So as we know from array processing theory that when a grating lobe occurs, the the main lobe peak also decreases. That's why we see that that's why we see that the peak gain is lower for most of the angles except this one angle which is minus 5.7 degrees. So this shows that operating DM in a narrowband setting is actually suboptimal. So we propose this new direction where the DMA can be configured optimally by changing the operating frequency itself. So we can vary the operating frequency in a feasible spectrum, which is envisioned for the DMA. And for each angle, we can propose a new operating frequency which can be dynamically configured. So if you're familiar with the frequency hopping technique in CDMA, where the the spectrum of communication changes dynamically depending on the channel condition. So it's a similar analogy where we can create frequency dependent beams by changing the operating frequency of communication. So in our work, we show that the dominant beam direction and the operating frequency of the DMA are intertwined through the DMA's frequency response. We design a DMA that attains the maximum beamforming gain, like the true time delay array, in the desired beamforming angular range. Let's look at the model of a single DMA at the transmitter. So the transmit signal is input to the waveguide from one end and it leaks out through these rotating slots. Here we make two assumptions. The first assumption is that we assume in the model that there is no magnitude degradation and only a phase advance as the signal propagates through this waveguide. And second, for simplicity, we assume that the receiver is in a line of sight channel. So let's look at how we can express the electric field at the receiver at a given angle phi and distance r. So we can write the electric field as summation of the contribution of different slots. And the contribution of different slots is governed through this term called as magnetic polarizability that gets multiplied by this phase term over here. So this phase term has two contributions. The first contribution is from the intrinsic phase that depends on the waveguide refractive index and the interelement spacing. And the second component is the extrinsic phase, which depends on the beamforming angle. Let's look at what are these beamforming weights here. So the beamforming weight is governed through this magnetic polarizability, which depends on the resonant frequency. So as I discussed earlier, the resonant frequency changes the electrical length of the slots, and that changes the beamforming weight for each slot. An alternate representation of this polarizability is in this form, where we have this term which depends on the phase angle. So we see that this polarizability depends on the sign of the phase angle as well as this exponential term. So the phase angle appears in both the magnitude and the phase. This is unlike a conventional analog beamforming where you have a unit modulus constraint. So in a phase shifter, we get uniform magnitude but different phases, whereas in a DMA, this blue curve shows that there is coupling between the magnitude and the phase. So this complicates the beamforming optimization problem. So there is some prior work which addresses this coupled magnitude phase constraint. However, that solution is only for a fixed frequency. And as we saw earlier, that operating at a fixed frequency for a DMA is suboptimal. So we take one step further where we jointly optimize the resonant frequency that govern the beamforming weights and the operating frequency in a feasible tuning range. In our paper, we propose closed form solutions for both the optimal frequency and the resonant frequency. So the operating frequency depends on the beamforming angle. And in the simple case of line of sight channel, we observe that the resonant frequency is same as the optimal operating frequency for each slot. we can express the beamforming gain in terms of this function here, which depends on the beamforming angle. So let's look at in what conditions we can get the maximum n squared gain. So we see that in this plot, this n squared gain is possible only in this uh, regime of 60 degrees. And that is because the DMA has a specific operating frequency. In this plot, it's 12 to 18 gigahertz. And if the solution uh, so this dashed curve shows that that's the unconstrained optimal frequency. Whereas if we constrain the optimal frequency, then the operating frequency gets clipped at these two limits, and that's why we see that the peak beamforming gain drops outside the desired angular range. So let's look at why this solution exactly works. So as I showed earlier that if we operate the DMA on a fixed operating frequency, then we observe grating lobes. Whereas if we configure the DMA by changing the operating frequency itself, then the grating lobe coincides with the main lobe and thus the peak gain becomes higher. So this is like a graphical demonstration of the two approaches. So in the fixed frequency approach, the optimal frequency is fixed to a center frequency, whereas in our approach, we are dynamically changing the operating frequency as function of the beamforming angle. And that's why we get the maximum peak beamforming gain in the desired angular range. So how does this affect the overall end-to-end achievable rate? So the rate depends on the SNR and the SNR depends on the beamforming gain. So in this plot, we show the achievable rate as function of the DMA tuning range. So far we were looking at this range of 12 to 18 gigahertz, but let's see what happens if we vary the tuning range on the x-axis. So the red curve is the upper bound, which is the true time delay benchmark that is always optimal in the wideband case, whereas the green curve is the proposed approach. So we see that for lower tuning range, there is a huge difference in the proposed approach and the upper bound. Whereas if the tuning range increases, then we see that the achievable rate of the DMA also increases and it approaches the true time delay benchmark. It also significantly outperforms the fixed frequency benchmark that was done in the prior work. So we see that with higher tuning range, we are able to achieve similar performance to the true time delay architecture. But since DMAs are energy efficient, so uh, that's why they can be an alternative solution to replace the power hungry TTD arrays in the base stations. So to summarize the key takeaways, in our work, we have shown that dynamic operating frequency reconfiguration for a DMA improves the beamforming gain compared to the fixed operating frequency approach. And if we use a DMA with wider frequency tuning range, we are able to achieve data rate comparable to the conventional power hungry true time delay array. So DMAs are a potential low cost and low power candidate for the next generation wireless beamforming. You can check out this journal paper for more details. Some other ongoing work in our group on DMA includes developing a single shot beam training approach where we can use an array of DMAs to estimate the receiver direction by just sending one OFDM symbol. And we can use this property that since it creates frequency dependent beams, we can probe multiple directions simultaneously using just one OFDM symbol. The second contribution from our group is on developing frequency reconfigurable ad hoc networks. So in a military setting where there are multiple interfering nodes, we can cancel out the interfering nodes by using this frequency reconfiguration property. Thank you, and I look forward to your questions and comments.